Okay, in this video, I'm working through a toy problem of a parking lot sensor. So to describe the problem, let's say we had cars. All right, so I'm going to mark these in green. Here's a car, and here's a car. And we're trying to display how many open spaces are left in the parking lot. So this is a scaled down version of the problem. For the problem in consideration, it actually doesn't matter how big the parking lot is because we're displaying the number of empty spaces. But I suppose there is a maximum number of empty spaces depending on how many bits we allocate for the display register. So I'm going to decide on 8 bits, 7 down to 0. That's the normal way to do it with backwards. 7 down to 0. So 8 bits. So that would mean, we would have at most 128 empty spaces. Okay, so you get the idea. In this case, there's only 8 spaces total, and 3 of them are occupied by cars, and so the display should show 5 spaces. Okay, so hopefully you get the idea of the problem. All right, so what's typical for the toy problems in this class is we have a reset signal, but we're going to assume that's basically used to power on the device. And with a differential system like this, if you think through differential systems where you're counting things in a differential manner, it's a little more problematic because if there's some type of error, your system gets off and it's hard to calibrate that. Okay, so we're not going to pay attention to those kind of details. We're going to assume the sensors are perfect and we're getting a perfect initial condition and perfect reaction from the sensors so we can perfectly detect exits and enters into the parking lot. So in real life, you'd need some error checking on this. You'd also probably have a calibration mode. Okay, so we're going to assume that somehow, initially, you can program a register or some switches or something to indicate how many empty spaces are initially present before you start operating the device. Okay, so we have a reset signal showing here, but we don't need to specify that anyplace else in the problem because we would assume that basically if you hit reset, you're starting over. Okay? All right, so from there, let's finish off the high-level state machine because I want to take the approach of looking at high-level state machine to data path to finite state machine controller down to circuit. So for this video, we're going to focus mainly on the high-level state machine. So I've already got this started. I had a reset state. And if you think about it, you're going to need to set the display counter, okay, the thing that shows the number of spaces, you're going to need to set that to some value. Okay, so let's assume that initially we have m empty spaces. M is equal to the number of empty spaces initially. Okay. All right. So then the very first thing we do on the next clock pulse is we're going to go to another state. We could call that something. Let's call it P for processing. Okay. So in this processing state, we're waiting for signals. All right, and so one thing that could happen is that we could have a car comes in, and another thing that could happen is a car comes out. So if I had a car coming in, what would I need to do? If I have a car coming in, I'm going to lose an empty space, so I would need to decrement the S register. If I had a car coming out, I would need, so D for decrement, I for increment. If I have a car coming out, that frees up an empty space, and so S is equal to S plus 1. Okay, but it's a little more subtle than that because let's think about these inputs, car in and car out. Based on the diagram, could you have a car coming in at the same time that you have a car coming out? And I guess the odds of that would depend on the speed of the clock. If it's a really fast clock, then the odds of those lining up would be less. But if you had a really slow clock, like a 1 minute clock, oh yeah, it'd be pretty easy to get a car coming in and out at the same time. So once I think of that, I think, oh gosh, since I could have car in and out at the same time, this state diagram has a problem. Do you see it? It's a problem because if you had car in and car out at the same time, this would go to two different states, and this wouldn't be a valid state diagram. So of course, how you'd fix that is you would add some logic. So we could make this dependent on car out prime, and this one car in prime. So as long as you have car out and not car in, you're going to increment. If you have car in and not car out, you're going to decrement. Okay, so what would happen in the other cases? If I didn't have car in or car out, I would just stay and not increment or decrement. I could just stay in P, all right? So I can either show that, or I can just assume that that's a loop back that's not shown, and that's what I'm gonna do here. I'm not gonna show all the loop backs. If I had a car coming in and a car coming out at the same time, then I would decrement and increment and essentially not change anything. So it'd be okay to just stay in state P from there. Okay, so once you have the car coming in, you decrement, you'd go right back to processing. Same thing here. If you had a car coming out and you incremented, you go right back to processing. So that would be a transition of logical 1. Okay, so this is a high-level state machine. I'm processing what happens in the register S. S equal -1, S equals +1, and S is equal to M. Depending on the states, I tell what the input transitions are. From there, I would need to find a data path to support this. All right, so that'd be the next video.